Good morning, dear students. Welcome to another session of Verilog HDL. So, in the previous session, we started off with the discussion of gate level modeling. So, in which we have discussed the gate types and slash or gates. Then we discussed how we instantiate those, and then we discussed regarding buff slash not gates. And a slight variation with respect to this, that is based on conditions. Also we checked out, that is buff if 0 and buff if 1. So these also we have discussed. We started off, we also discussed one example related to gate level multiplexer, how it is implemented, and the same concept was applied for 1 bit multiplier, and later using that 1 bit multiplier we developed the 4 bit full adder, 1 bit full adder. Using that 1 bit full adder we developed 4 bit full adder. So that is what we have discussed in the previous sessions, and we had started off with a discussion of the delays. So these are the things what we had discussed. So coming down to delays, there are three types of delays, that is rise, fall, and turn off delays. What is meant by rise delay? It is nothing but uh, you can be in any state, say 0, X, or Z, that is the system can be in, the output can be in any state. The time required for the output to change from any previous state to logic 1. So that is what a rise delay implies. That is, in this case, we can just see that the rise delay is associated with the gate output transition to 1. And previous this thing can be any another value. So the gate transition from any of its previous state to it transition to a 1 will give rise delay. Then what is meant by fall delay? It is nothing but the opposite of your rise delay, what we specify. It is the gate transition to 0. It is a gate, it's the time taken for the gate to transit from its previous state to 0. Then turn off delay. Turn off delay is basically associated with the gate output transition to high impedance. That is, gate has to reach high impedance state. Gate output should reach high impedance state. So these are the three things what we had discussed. Rise delay from its previous state, 0, X, or Z, the time taken for it to reach logic 1 or the gate output transition to 1. Similarly, fall delay is related to the time taken for the gate output to transit from its previous state to 0, and turn off delay is the transition time which is taken by the gate output to reach high impedance value. So these are the three types of delays what we have and how we specify those delays. So in this one, so how do we specify delays in the gate level modeling? So here we can see we have specified, we have used the the keyword and then we use hash, and in the brackets we specify the delay time. Now we can do it in three different forms. So here we can see that only one delay has been enabled. Only one delay time is specified. Whereas here, if we just see, we have two values which are separated by a comma. Then here we have three values which are separated by a comma. So the way remains same. Just remember that you are separating the delays with a comma value, a comma specification. So here, what we have here we can see that if I specify only one delay, if I specify only one delay, then what is its implication? So if I specify one delay, this value will be utilized for all the transitions. That is for rise delay, fall delay, and turn off delay. All will be having the same transition time which is required. Now, if I specify two values, right, then what it implies is For the first value will be related to the rise delay, and the next one is related to the fall delay. Next one is related to the fall delay. Now what about the turn off delay? So the turn off delay will be lower of these two. Turn off delay will be lower of these two. Then last one, rise delay, fall delay, and turn off delay. So this is if all three are specified, all three can have separate values, same values, so depending on what value you are specifying. So examples are related to the same as given here. So here we can see that we have specified for the AND gate a delay of 5 time units is been specified. So here this delay will be applicable for all the transitions. That is 5 time units delay will be applicable for all rise time, fall time, and turn off delay. So in the next one, we have two values which are separated by a comma, 4 and 6. So in this case, rise time will be taking 4 time units and fall time will be taking 6 time units. Now what about the turn off delay? The turn off delay will be lower of these two. That is, it will be 4 time units which it will be consuming. Matar. So here we have three delays which is specified 3, 4, 5. So we have the first one specifies the rise delay of 3 time units, next one fall delay of 4 time units, and turn off delay of 5 time units. So this is how we specify. So here one important thing to just stress out is you can see that the values are separated by a comma. So now next one is the values which are being specified for the delays. So we can have three different type of values assigned to the delays. We can have a min type of minimum values, maximum values, and then we have something called as typical values. So now what does these specify? So this is all again as per the designer's requirement. They can put forth what delay you can utilize. So here we can see that the min value gives you the minimum delay that is required, and this will be specified by the designer. He can put forth these things. So the transitions for the gate transitions, what should be the minimum delay? So that is specified by min value. Then there is one condition which is called as typical delay. So that is it is termed as TYP value. So which is typical delay value. Now again last one we have max value. So which basically specifies the maximum delay value which the designer can provide. So these are the different types of values which are provided by Verilog runtime. Now, how do we specify these delays? So these delays are actually specified during the runtime. They are specified during the runtime. You are not specifying it during the compile time or any other time. You are specifying it during the runtime. So if I want to clarify this, right, you can just observe the code over here. So you have written a Verilog module as say test.v. The module consists of everything. Now you are calling Verilog test.v. So this will run the test.v file. It will run this module. Now along this you can, if you just run it, it is not a problem. And if you want to specify the delays, right, you can specify those delays. So here you can see that Verilog test.v plus max delays. So this delay is specified during the runtime. It is not specified in the code. But what are the values you'll be specifying in the code what you are writing? So during compile time, you don't have control on identifying which one you'll be choosing. So it is during the runtime what you'll be providing. So these are the different types of values which are provided for the delays what we have discussed over here. Okay. So again, we have min value, that is minimum delay, a TYP value, that is typical delay value, then max value, which is maximum delay value. So these are all again designer oriented, and designer can provide these delays. So how do I provide this information over in the Verilog? So here we can observe, we have to compare it with the previous case. So let me just compare it over there. So let me come to the first part. So here, for example, what we had specified only one delay. That is whether it is rise, fall, this thing. Only one delay value we have specified. Example is this one. So wherein 5 time units is for all the transitions. So 5 time units. But now I want to specify, along with this, I want to specify instead of 5, what is the minimum delay, what is the maximum delay, what is the typical delay. So if I come down to this example, right, here. So we have and hash. Here we can see that we have specified 4 is to 5 is to 6. So what is this specifying is minimum delay should be, can be 4 time units. Typical delay can be of 5 time units, and maximum delay can be of 6 time units. Now, since only one value, one this thing you are specifying, the same thing will be applied for all this thing, that is rise, fall, and turn off. So it will be applied for all three delays what we have discussed. So these values will be applicable to all three delays. Minimum will be 4 time units, typical will be 5 time units, and maximum will be 6 time units. So that is what you are checking out here. Now coming down to the next one. So in next one, what we had and hash, and we provided two different values separated by a comma. So the first value was related to rise, rise, rise time, and the next one was related to the fall time. So now here we can just see we have and hash. So here we can see that it is 3 is to 4 is to 5, and comma 5 is to 6 is to 7. So what is this specifying? So this part 3 is to 4 is to 5 is for the rise delay, and this part is for the fall delay. Now what should be the turn off delay? Turn off delay will be the smaller of these two. Now for example, during execution, I have specified that you will be using, say, you'll be using say maximum delay. So maximum delay in the rise time is 5 here, and maximum delay in this one is 7. So minimum of these two is what? 5. So 5 will be the typical delay value. Since only two we have specified, in first case, this will be applied to all. But in next case, this will be applied for rise delay, and this will be applied for fall delay. So here we had just single values and 4 comma 6. So 4 time units or 6 time units, that is rise and fall. So minimum of these two was 4. Now instead of just specifying one, we are specifying three different, that is what should be the minimum delay, maximum delay, and the typical delay. So what are the three values it can take over? That is what we are specifying here. Okay. So this is for rise time, this is for fall time. Now the last one, what is present is we had provided all three values. So rise value, fall value, and turn off value, all are separated by comma in this case. So the example is over here. There is 3, 4, and 5. 3 is the rise time. 4 is the 4 time units is for fall time, and 5 time units is for turn off time. So here all three delays are specified. Now, what are the values it can take? So here you can see that 2 is to 3 is to 4. So this is for rise time. This is for rise time, minimum, typical, and maximum delay. So similarly separated by comma, next comes the fall time. So it is 3 is to 4 is to 5. So 3 is the minimum delay, 4 time units is the typical delay, and 5 time units is the maximum delay. Next we have 4, 5, 6. So 4 is the minimum delay, 5 is the typical delay, and 6 is the um, maximum delay value. So this is how it goes around. So this is for rise time, this is for fall time, and this is for turn off time. So now how do I invoke these? So which delay I have to utilize? How do I invoke them? So you write the entire stuff and you save the file. So once you save the file, if you have to run it, you go for stimulus this thing. So wherein you do in that form or you invoke the simulation. So Verilog test.v. So when you type and enter this, it will be invoking the entire test.v file and it will be simulating the results. Now, during the simulation, what should be the rise time, fall time, and turn off time of the gates which are involved in it? So if I don't specify anything, and I have mentioned all these values, I have mentioned the values, I have mentioned these values, then what is done is typical delay values will be assigned for the rise, fall, and the turn off delay. If I don't specify this one, right? If nothing is specified, by default, it is the typical delay values what will be utilized. But if you want to specifically mention which delay you have to utilize, then you go ahead and use the keywords plus max delays plus typical delays plus min delays. And this is done during the runtime. So here we have, so this file will be utilizing the maximum delays. For example, I have specified this. So in this one, maximum delay for rise time is 4, maximum delay for fall time is 5, and maximum delay is 6 for the turn off. So these are the values what will be utilized when the simulation goes around. Similarly, we can make use of the other values. If nothing is specified, by default, typical delays will be utilized. Delay values will be utilized. Now we have an example over here. So here, this is the expression what we want to realize. And here we can see that output is equal to AND operation of these two inputs and ORing of the overall result with C. So ORing of overall result with C. Now in circuit, right, when we rig up the circuit, we have observed that when we say change A, it will take some amount of time and get displayed at the output if changes are happening. If you change any of these inputs and if change has to be happened at the output, it might take some amount of time. So that is what you are trying to represent using delay and the delay values. Now here what we are assuming, say the AND gate consumes about 5 time units and the OR gate consumes about 4 time units. So this is the amount of time which is which these gates are going through. So now how do I go ahead in writing this in the Verilog? So here we have module D. So D is the name of the module. This is the parameter list. So output ABC. Then sorry, the port list or the terminal list, then the declaration. So this one is the output and these are the inputs. So that is what you have specified. And internally you can see that this gate requires a connection from the previous AND gate. So whereas C is directly connected to this one. So this wire I have to specify, that is net data type I have to specify. So wire E is mentioned over here. So this tells how the circuit is made up of. Now I need to instantiate these things. So what is the first this thing? AND, which takes inputs A and B and provides the output E. And there is a delay of 5. So previously, if you had seen what you had written, you had just written, you would write it as AND say you would specify the name of the module, or you would keep it as it is. So you had seen that. See, I'll just specify it as and A. Output of this one is E, and inputs are A and B. So this is what we had specified previously. Now we specify this along with the delay. So here we have and hash 5 time units. Now we have specified only one delay value, right? So this delay value will be applied to all rise time, fall time, and the turn off time. So here we can see we have A1, output is E, that is output is E, input is A and B. So this gate consumes about 5 say time units for its rise time, fall time, and turn off time. Now next we have the OR gate, which introduces 4 time units of delay. So here we have connection input E and C, and output is out. So that is what is specified. Or what is the delay, which is 4, that is related to this one. Then we have O1, result is out, and inputs is E and C. So there is a delay of 4 time units introduced in the OR gate. So this is end of this module what you have defined. Now how do I stimulate this one? So again, so this is a top level module, and in this case we can see that there is no say input, that is the port list. There is no port list, but we can declare the variables as to assign them to the appropriate input to this entire stuff. So here we can see that we have declared something as register data types A, B, C, and there is a wire which is out. So now D is the name of this module. I have to instantiate this module within this stimulus block. So D, that is a module name. D1 is the instance of this module. Instance of this module. And what are the parameter? What are the ports you will be passing on? It will be out, A, B, and C. So it is out, A, B, and C. This is the output port, and these are the input ports. So now we have instantiated the module D. We have instantiated that. Now let us begin and see what happens with the simulation. So when we go ahead with the simulation, right? Now what I'm specifying here, what is the value of A? So here it is 1 bit in length, it is binary in its nature, and the value is 0. B is 1 bit in length, binary in its nature, and its value is 0. C is also binary value 0. So when this is the case, what happens to the output? That you can check out through the truth table of this one. So when any one of this is 0, output is 0. If any one of these inputs is 1, then only the output is 1. So in the first case, all are 0, therefore output also will be 0. So next, after 10 units of time, you are changing A to 1, B to 1, and C to 1. Similarly, again, after 10 units of time, you are keeping A as it is, but you are changing B and C to 0. And at the 20th time unit, you are changing it. So total, you can see that there are total 40 time units. Now let us come over here. So you started off at time 0. At time 0, what you made A was 0, B was 0, and C was 0. Now again come down to this block. So A was 0, B was 0, C was 0 at the first time unit. At the first time unit. Now in this case, when will E be available? E will be available after 5 time units of delay. So E will be available only after 5 time units of delay. No matter at t is equal to 0 you have applied, but at t equal to 5 you will get the value of E. So that is what is being displayed over here. So here previous value of E is unknown to me, but after 5 time units, so you can just observe here, after 5 time units, E value will change based on A and B. So since both are 0, what will be the value of E? Value of E will be 0. Now here C was 0, this was unknown, this was unknown. But this changed its value when? After 5 units of 5 time units. So once this has changed its value, after another 4 time units, then only the output will be available. Then only the output will be available. So now what happens in this case? So after E changes after 5 units of time, then once E has changed, it will take another 4 time units for the output to be reflected. No matter what is the output, it might be 0 or 1. So in the initial state, we'll be just assuming unknown value. So here we can see that at 5 time units, E changed its value. So this goes as input to the OR gate, which is present in that circuit diagram or the logic diagram. So after 4 units of time, that is 5 plus 4, that is 9. So at that moment, ninth moment, the output changes. So previously, I don't know what is the value. Now, what will be the output? It is 0, 0, 0. So E turned out to be 0, 0 odd with 0. That is E or C. It is E odd with C. So the output also should be 0. Output will be 0. So now in code, what you did? So you started off and in this time unit, the output changed. But after 10 time units, what you're doing in this line of code, after 10 time units, you are changing the values of A, B, and C. So you're making all ones. So when you make all ones, what happens? So A is changed, B is changed, C is changed. So at the 10th time unit. So that is what the first, that is the line of code is specifying. So all three are changed. Now, but this change to be reflected. So it is made 1, 1. So 1 ANDed with 1 is how much? E should be 1. But E will be 1 when after 5 time units have been passed. After 5 time units have been passed. So that is what they provide here. So here we can see that A, B, C is there, 1 and 1. So E will be changing its value after 5 time units from this point, that is at 15 time unit. 15th time unit, it will change. It will not change before that. But here another thing to identify is since C is another input to the OR gate. C is another input to this OR gate. You can see that C has changed at 10th time unit. C has changed at 10th time unit. So since there is a change in C, this XORed with this will give you a result after 4 time units. So here, what is happening? C has changed at this point. So since C has changed its value, but E hasn't changed. So since there is a change over here, what happens? The OR gate will give you a result after 4 time units. That is at 14th time unit, you'll be getting an output of 1. You'll be getting an output of 1 at this. Now, but again, remember what is happening. Again, here we can see that at 15th time unit, E value is changing to 1. E value is changing to 1. So since E value is changing to 1, what happens is 1 XORed with 1 is now 1 XORed with 1 is 1 itself. So there is no change in the state, but that will be reflected actually after the 20th microsecond. Sorry, it will be reflected after 4 time units, not 20th. 15 plus 4, 19th microsecond, 19th time unit. But that is not shown because the state remains same. That is not being displayed. But since there is a change in the value of E, the gate after 4 time units from this point at 19th time unit, it will show that it is still 0. Output is still 0. And this keeps on continuing. So this is how the simulation has to be analyzed when you are writing the code with the delay specifications. Okay. So that is in short, they have specified these all things.